12 years? That's how long a privilege escalation bug sat in the Linux kernel before anyone caught it. CVE 2026-31431, being called copy-fail in most write-ups, was introduced in kernel 3.16 back in 2014, and it gives an unprivileged local user a reliable path to root on affected systems. CVSS score is 9.8. That's not marketing rounding. The scoring reflects that exploitation requires no special privileges, no user interaction, and works across a wide range of kernel versions and architectures. If you're running anything between kernel 3.16 and 6.8.4 and you haven't patched yet, you have a problem. Let's be precise about what this actually is, because the press coverage has been a bit loose. Copy-fail is a use-after-free vulnerability in the kernel's copy-on-write page handling logic, specifically in how the kernel manages memory mappings when a process forks, and then attempts to write to a shared page. The flaw allows an attacker to manipulate reference counts on page table entries in a race condition window. If you win that race, and researchers say it's reliably winnable on modern multi-core hardware within seconds, you get a dangling pointer you can turn into arbitrary kernel write. From there, the standard playbook applies: overwrite credentials structure, escalate to UID 0, and you own the box. The phrase reliable exploit is doing a lot of work here, and it's worth dwelling on it. A lot of kernel CVEs are theoretically exploitable, but require specific hardware configurations, precise timing that doesn't hold up in practice, or kernel mitigations like SMEP and SMAP that break the chain. Copy-fail has working public proof-of-concept code that bypasses those mitigations on x86-64. The researchers who found it, a team at a security firm called Horizon Security, unclear from the reporting whether they have any vendor relationship that colors the disclosure, tested it against stock Ubuntu 22.04, Debian 12, RHEL 9, and a vanilla Kubernetes node running kernel 5.15. All fell. They're reporting median time to root of under 90 seconds on a 4-core VM. That's the number that should be making your incident response team uncomfortable. Now let's talk about where this actually hurts, because the threat surface here is not symmetric across all Linux deployments. The highest risk scenario is multi-tenant compute, anything where you're running workloads from different customers or different trust levels on the same kernel. Classic examples: shared CI/CD runners, VPS providers, university HPC clusters, any SaaS platform that gives users shell access or the ability to run arbitrary code. If tenant A can get code execution on the host kernel, tenant B's data is now tenant A's data. This is not a theoretical concern. It's the entire reason container isolation exists, and copy-fail punches through it. Speaking of containers, Kubernetes environments are specifically called out, and this is where a lot of engineering teams are going to feel it. Containers share the host kernel. That is not a bug in Kubernetes, it's the design. Namespaces and cgroups give you process isolation, not kernel isolation. A container running as a non-root user that can trigger this race condition can escape the container entirely and own the node. From the node, depending on your RBAC setup, an attacker might be able to pivot to the API server or access secrets mounted from other pods. If you're running privileged containers or host path mounts anywhere in your cluster, and a lot of shops do this for legitimate reasons, the blast radius gets larger. CI/CD pipelines are the third high-risk surface, and this one is underappreciated in the coverage so far. Think about what a typical CI runner does. It checks out code from a repository, possibly from a public fork or a PR submitted by an external contributor, and it executes that code with relatively broad system access. GitHub Actions self-hosted runners, Jenkins agents, GitLab runners in shell executor mode. These are all environments where untrusted or semi-trusted code runs on a shared kernel. If an attacker can get a malicious commit into your pipeline, copy-fail gives them a path from code runs in CI to code runs as root on your build infrastructure. From there, they can exfiltrate secrets, tamper with build artifacts, or pivot into your internal network. Supply chain attack surface, basically. The patch situation is actually not bad, which is the one piece of good news here. The fix landed in kernel 6.8.5. Major distros moved quickly. Ubuntu has patches out for 20.04, 22.04, and 24.04. Debian patched stable and old stable. Red Hat issued an advisory for RHEL 8 and 9 with a kernel update. SUSE has patches in their maintenance channels. The kernel versions you're looking for are 6, 8, 5 and above for upstream, or the specific distro backport versions listed in each vendor's advisory. Check your distro's security tracker, not third-party summaries, because the backport version numbers vary. For Kubernetes specifically, you need to patch the node kernel, not just the container image. Updating your pod's base image does nothing here because the vulnerability is in the host kernel. If you're on a managed Kubernetes service, X, GKE, AX, check your provider's advisory. As of the time this script was written, Google had already rolled patches to GKE nodes in standard and rapid channels. AWS and Azure had advisories out, but rollout timelines were unclear from the reporting. If you manage your own nodes, this is a kubectl drain, patch, reboot cycle. There's no live patching path for this one because the fix touches core memory management paths. There's also a kernel mitigation worth knowing about if you can't patch immediately. Setting the kernel parameter VM, unprivileged user fault to 0, and disabling unprivileged user namespaces via kernel. Unprivileged users clone reduces the attack surface significantly. It doesn't eliminate the vulnerability, but it breaks at least 2 of the known exploitation chains in the public POC. On systems where those features aren't needed for legitimate workloads, that's a reasonable temporary measure. On Kubernetes nodes, unprivileged user namespaces may be required for certain container runtimes, so test before you flip that switch. One thing the press coverage has been somewhat breathless about is the 12 years undetected framing, and it's worth adding context. The bug being present for 12 years doesn't mean it was actively exploited for 12 years. There's no evidence of in-the-wild exploitation before the public disclosure, though absence of evidence isn't evidence of absence, especially for a race condition that doesn't leave clean forensic artifacts. What the timeline does tell you is something we already knew. The Linux kernel's security review process has gaps, particularly in memory management subsystems that are complex and don't get the same scrutiny as network-facing code. This isn't a novel observation. It's the same lesson from Dirty COW in 2016, from Dirty Pipe in 2022. The pattern is consistent enough that if you're running multi-tenant Linux and you don't have a kernel patching SLA shorter than 72 hours for critical CVEs, you should probably fix that process, not just fix this bug. The actual takeaway here is mechanical. Run your package manager against the security repos right now, verify the kernel version after reboot, and if you're on Kubernetes, check your node pool versions before you check anything else. If you're on a managed cloud, open the provider console and look for pending node updates. Don't wait for the automated rollout window. And if you have self-hosted CI runners that execute code from pull requests opened by external contributors, either move those to ephemeral VMs that get destroyed after each job, or treat patching them as an incident-level priority, not a maintenance window item.